Welcome back to the lectures in Journey of Mathematics. So today let us discuss about understanding eigenvalues and eigenvectors. So let us start our lecture now. Okay, first let us discuss about the definition of eigenvalues and eigenvectors. Okay, so if you take a matrix A of n by n, that means it should be a square matrix. Next, I am taking another vector that is n by 1. Okay, it should contain n rows and 1 column. Okay, a non-zero vector v in an n-dimensional vector space is called eigenvector if it satisfies this condition. If it satisfies, the product of A with the given vector should give the result as some scalar product with the given vector. Okay, and that scalar lambda is called eigenvalue and the vector v is called eigenvector. Okay, so let us understand this definition in a graphical way. What is the graphical meaning of this? Okay, so a vector that undergoes pure scaling without any rotation is known as eigenvector, and the scaling factor or the stretching ratio is known as eigenvalue. Okay, so what do you mean by scaling and rotation? Okay, so let us understand this by a practical example. Okay, so here I am taking a matrix A, that is n by n matrix, square matrix. Okay, I call this matrix as moment matrix or transforming matrix. Okay, so I am taking the product of this matrix with a vector, we call it as input vector. Okay, so let us draw this input vector in a graphical manner. So what happens? So if you draw in a graph, you will get this point. So and draw a vector from origin like this. Okay, so what is the product of these two matrices? You will get again n by n by 1 matrix. Here 2 by 1 matrix is there. If you multiply with the 2 by 2 matrix, you will get 2 by 1 matrix. So what is the product of these two? So how much you will get? 5 into 4 you will get, 5 into 2 you will get 10, 4 into 3 you will get 12. So 10 plus 12 you will get 22. So this is correct. Next, 3 into 2 6, 1 into 3. So 3 into 2 6 and 1 into 3 we get 3, 6 plus 3 9. So this is also correct. So again I am drawing this vector 22 9 in a graphical manner. So it looks like this. So what you have observed, whenever you are multiplying with the given matrix with the input vector, the given vector has been scaled. That means this vector has been stretched like this. Okay, stretched and has been rotated like this. Okay, it has moved from origin place to another place. That means it is rotated and stretched. Okay, so I can call this vector as non-eigenvector. Okay, so let us see one more example with another input. Okay, what happens? So this vector has been scaled and rotated. So now I am taking one more input vector with the same matrix, and if you draw this vector in a graphical manner like this, so you'll get vector. Next, if you multiply these two, again you'll get 2 by 1 matrix. So how much you'll get? 5 into 2 10, 4 into 1 4, so you'll get 14, 3 into 2 6, 1 into 1 1, so you'll get 6 plus 1 7. So this product is right. Okay, now let us draw the output matrix whichever we got this. Okay, so I am drawing that. So what happens? So it has not been rotated, but it has been stretched like this. Okay, so this is what we have discussed in the previous slide. Okay, the vector which is not rotated and has been only undergo through scaling. Okay, so the output vector has been only scaled but not rotated. Okay, such kind of vectors are called as eigenvectors. Now, according to our definition, what we have written? A into V is equal to lambda V. So here V is nothing but this X. Okay, so how to match with this given definition? Okay, A into V I have written like this. What is V here in the right hand side? So let us take the common 7. So if you take 7 common in this matrix, so how much will get? 7 into 2 will get. So that means 2, 1. Okay, so does it match with this or not? Okay, A into V, you got 7 into the same vector. Okay, here 7 is called the scaling factor and this 7 is called eigen value. Okay, so I think you have been understood the difference between non-eigenvector and eigenvectors. Okay, so let us take one more practical example in a real life. So if you take a certain bridge, hanging bridge, what happens if the more vehicles are passing through on it than its capability? So what happens? The bridge will shake. Correct. So this moment caused by these vibrations, okay, due to the some external force, okay, it will rotate. That is called our matrix A, which you have seen. If it reaches the eigenvalue and eigenvector, what happens? It will collapse like this. Okay, so this is one more example. That means whenever a moment happens and when it reaches the eigenvalue or eigenvector, okay, it start stopping rotational force and it will be going on stretching. So if you are getting more stretch, what happens? Anything will be collapsed. The same eigenvalue and eigenvector concept will be used while doing driving a car. Okay, so suddenly what happens? If you are rotating more at one particular stage, it will reach eigenvector position. So and it won't be rotated. So what happens? It won't be rotated. It try to stretch. So the gear parts will be smashed. So with this, I'm going to close my lecture. Thank you for watching. So I hope you enjoy the lecture. Thank you.